Welcome to The Explainer. Today, we're going to pull back the curtain on how we get from a chaotic mess of data to the intelligent AI that's changing our world. It's basically the journey of building a thinking machine. So let's dive right in.
All right, let's kick things off with a number that's, well, it's pretty much impossible to wrap your head around. 500 terabytes. Yep, that's what Facebook cranks out in new data every single day. And look, it's not just Facebook, right? It's happening absolutely everywhere. This is the world we live in now, this massive, overwhelming flood of information we call big data. Think about it, a tidal wave of tweets, videos, transactions, you name it.
So the big question is, how on earth do we even start to make sense of all this chaos? Well, to navigate this flood, experts have this framework they call the 5 Vs, and that's going to be our map for this whole journey.
Okay, first up is volume. This one's pretty obvious, right? It's just the sheer scale of the data. And to give you some perspective, a single zettabyte, just one, could store 30 billion 4K movies. Yeah, we are talking about an astronomical amount of information here. Next, we've got velocity. See, it's not just that there's a lot of data, it's that it's coming at us at an incredible breakneck speed. Think about a live stock market feed, or the fire hose of tweets during something like the Super Bowl. That data has to be captured and processed, like, right now. All right, then there's variety. So if your traditional structured data is like a perfectly organized filing cabinet, then all this new unstructured data is like a giant messy pile of photos, audio clips, and social media posts. It's chaotic, and our systems have to be built to handle all of it. Then we have veracity. This V asks a really simple but absolutely critical question. Can we even trust this data? I mean, just imagine a self-driving car getting bad info from its sensors. The stakes can be incredibly high. So veracity is all about making sure the data is accurate and reliable. And that brings us to the last and honestly the most important V of them all, value. Because let's be real, if all this data doesn't lead to something useful, some kind of meaningful insight, like a better recommendation on Netflix or a more accurate medical diagnosis, then it's all just digital noise, right? This is the whole point of doing any of this. Okay, so we've got our 5 Vs, we understand the landscape, but now we hit our first huge problem. You've got this mountain of data. Where do you even put it? I mean, you can't just save a zettabyte of data on your laptop, right? You need a totally different way of thinking about storage. And the solution that came along was this system called Hadoop. It basically works on what's called a master-slave architecture. So think of it like this. You've got the name node. That's the master, the brain of the whole operation. It doesn't actually hold any of the data itself, but it keeps this perfect, detailed map of where every single little piece is. And then you have the data nodes. These are the slaves, the muscles, the ones doing all the heavy lifting of actually storing all the files, spread out across a whole bunch of machines. Okay, and here's a classic trip-up, something that gets a lot of people. You hear secondary name node, and you think, a backup. But no, it is absolutely not a fail-safe. It's not a vice president waiting to take over if the boss goes down. Its real job is much less glamorous. It's basically just doing administrative cleanup, a process called checkpointing, that helps the main brain, the name node, stay organized and efficient. All right, so our data has a home now. It's all stored safely across our system. But raw data is pretty much useless, right? It's just sitting there. We need to process it. So let's move out of the warehouse and onto the factory floor. Now, the original assembly line for this whole factory was something called MapReduce. Here's a simple way to think about it. Imagine you had to count every single word in an entire library of books. The map step is like having a bunch of people go through and tag every word they see. Then, the shuffle step gets all the identical words grouped together, all the thus in one pile, all the ands in another. And finally, the reduce step just counts how many words are in each pile to give you your final result. But here's the thing about MapReduce. It was reliable for sure, but it was slow. It was kind of like taking the scenic route because it had to write everything down to the computer's hard drive after every single step. The industry needed something way faster. It needed a supersonic jet, and that jet turned out to be Spark. The big difference, Spark does its work in the computer's super fast memory, which can make it up to 100 times faster. A total game changer.
So this is all great for that nice, organized, structured data we talked about. But what about that variety V, remember? A lot of the data we have today is just chaotic. It's messy. It doesn't fit into nice, neat tables. So what do we do with that stuff? Well, that brings us into the world of NoSQL databases. The name literally means not only SQL, and they are all about flexibility. They come in like 4 main flavors. You've got key value stores, which are like a super simple dictionary for really fast lookups. Then there are document databases, which are great for storing more complex stuff, like a whole user profile. You've got Columnar stores, built for tearing through massive datasets for analytics. And finally, graph databases, which are all about understanding relationships. Think of a social network and how everyone's connected.
But there's a catch. This flexibility, this idea of running on tons of machines all at once, it forces you to make a really tough choice. There's this fundamental trade-off, and it's all summed up by something called the CAP theorem.
Okay, so here's the core idea. Let's say you're using your banking app, and there's some kind of network glitch. What do you want to happen? Do you want the app to still be available so you can at least see your balance, even if it might be a few seconds out of date? Or do you want it to be perfectly consistent, meaning it shows you an error message until it can guarantee 100% that the number you're seeing is exactly right? Well, the CAP theorem says that when the network gets messy, you can't have both. You can't have perfect availability and perfect consistency. You have to pick one. You have to choose what's more important for your specific situation.
All right, so let's recap where we are. We've stored our mountain of data, we've processed it. It's organized, it's accessible, it's ready to go. Now for the really cool part. It's time to build a brain on top of all of it. So we start with the biggest idea of all, artificial intelligence, or AI. This is the big picture dream, right? The stuff you see in movies. It's this broad concept of creating machines that can think, reason, and learn, basically just like humans do.
Okay, so zooming in a little bit, inside of AI you have machine learning, or ML. Now this is how we're actually building smart systems today. So instead of a programmer trying to write like a million if-then rules to teach a computer what a cat looks like, we just show the computer a million pictures of cats and we let it figure out the patterns on its own.
And then right at the very heart of the AI revolution that's happening right now, you'll find deep learning. This is a super powerful part of machine learning that uses something called neural networks, these complex, multi-layered structures that are kind of inspired by our own brains. This is the engine that's driving all the crazy stuff you see today, like your phone understanding what you say, or those AI systems that can create incredible images just from a sentence.
So how do these things actually learn? Well, it basically breaks down into 3 main styles. First, you have supervised learning. This is like studying with flashcards. The machine sees a picture of a cat, and you've already labeled it cat, so it knows the right answer. Then there's unsupervised learning. This is more like being a detective. You just give the machine a giant pile of data, and its job is to find hidden patterns and groups all on its own, with no labels to help it. And finally, there's reinforcement learning. This is a lot like training a dog. The machine learns by trial and error. It gets a reward when it does something right, and it learns from its mistakes when it does something wrong.
And there you have it. We've gone on this incredible journey, right? All the way from a chaotic flood of raw data through all the systems that store and process it to the point where we have a machine that can actually learn and predict things. We've essentially given data a brain. But that just leaves us with one final and maybe the most important question of all. As these incredible tools get more and more powerful, how do we give them a conscience?